moment it's still a decimeter, but I will remind you the assumption, but anyway, we are in dimension 3. Let's see figure 35. But at the moment I'm not using figure 35 yet. So the first step was, which we did yesterday, was the reduction to P of fields.
Why do we call them PL but not PLT?
Ask Shukuru. I really have no idea. Yeah, names are weird.
Because it's weird, like calling
So now we try to use again this type again. I'm not using very much the fact that this is 5, and we still do Shukuru. It's about reducing problem to lifting theorem. Existence of P of x. So what is the context? The context was, let's suppose that we have a pair, a log pair, which is P of t but not P of t. So in other words, we really have a component, at least one component of coefficient 1. Then, as usual, we have a P of flipping contraction, where, let me remind you, the most important thing is that the relative peak number is equal to 1. Then kx plus delta is eta negative, which again means that on any curve which is contracted, or on one curve which is contracted, kx plus delta is negative. And also we have one more assumption which will play a very important role in 1 minute, is that also S will be eta negative. Okay, how do we prove existence of flips under this assumption? Sorry, I should have said that eta is small. How do we prove existence of P of flips under this assumption? And this is the trick of Shukurov. Well, first of all, we may assume, since this is a local problem, we may assume, without loss of generality, that Z is affine.
And do we assume that S is contracted?
No, absolutely. S will not be contracted because it's small. So it will not be contracted. It's actually. So the idea is this.
Some part of S is contracted.
Some part of S will be contracted. The idea is this. We have a flipping curve which lies inside S, this way. So when you take, this is inside X. When you take the contraction, the flipping contraction, which I call it Z, what we have is that the surface S becomes outside. So the curve will be contracted 1. And what we want to do, more or less, this is vague, but more or less what we want to do is we want to contract X plus. And most likely, but it's not always the case, the picture will be like this. Sorry. It's not always the case, it could be still said.
Yes, but still, you need to ask, you need to know that my kx must go this way.
Yeah, that's right. So kx plus delta is eta negative.
Negative?
Yeah. Also S is eta negative. So in other words, yeah, let me just write it here. This is the P of flip. This is the flipping curve. So I'm assuming that both this is negative and kx plus delta is negative. But this is what is indicated. Okay.
So, and what is on the right picture is
most likely the strict transform of S, which I'm going to put it as plus, is not going to contain the flipped curve, but it will be intersecting. It will always surely intersect positively. So for sure, if this is X plus, this is going to be positive. So of course, it doesn't mean that this is true.
The curve is irreducible, or you don't really care?
You don't care. You don't really care. It could be more than one curve, but all equivalent. We're in dimension 3, so the picture is not too complicated.
Yeah, but S is irreducible, right?
S is irreducible, it's right. Yeah, it's right. S is irreducible because it's a P of T. that, first of all, what is the existence of fixed? So it's enough to show, this is true in general, even without assuming that it's affine, that the algebra given by all the multiple of Pezzo delta over Z is finitely generated. Sorry.
So F is eta.
F is eta, thanks. But now we are in a very convenient situation because I'm assuming that Z is affine. So actually, this is equivalent to show that this algebra here is finitely generated. I'm going to write what it is in one moment, but I think it's obvious. So it's exactly the same to show that this is finitely generated. So you see that the degree 0 of these two objects is exactly equal to A, where Z is equal to spectral. So A coincides with M equal to 0 both here and here. And again, the quality of these two is because Z is affine. Okay. How do we do that? And now we very much use the fact that the picard number of x is equal to 1. So since Z is affine, and rho of x with Z is equal to 1, let me just write first something which is weaker than what I need. There exists A and B such that A dx with delta is equivalent to B for the moment they're integers, but I'm going to be more precise. B times x. Okay? I want to be more precise, and I notice the fact that both of them have the same sign, or maybe we're writing this. So I can assume that they have the same sign. So in particular, I can assume that they're both positive integers.
So isn't it numerical equivalence?
Actually, linear equivalence. So it's more than
Well, I mean, is it in
model something coming from below us.
is it in a relative Picard group or is it
Yeah, but it
That's
is
the file.
the grid is affine. The grid is affine.
So it's affine, but it's still not.
Yeah, but you can make it a little bit smaller and then.
But then there might be a continuous part of it, so that we can't see.
No, it's okay because you can always assume that this one is over A.
Yes, over A. I can have a local ring whose Picard scheme is continuous.
Sure, but you can make it smaller, no?
I mean, I could complete the ring, and I could still have a non-trivial Picard scheme. I think you need to kill.
It's singular, yes.
But could we say? I mean, it may not matter.
Yeah, but it's something coming. Okay, let's see.
You can multiply both sides.
If we just say it's torsion,
Yeah.
maybe we're over FP bar.
No, but this is still really constant 0. So this is part.
When it comes at 0, you've got vanishing. And R1 A start the structure sheet is 0.
Okay, whatever the difference is, come from below.
Sorry?
Whatever the difference is, come from below.
so it's in the relative Picard?
So if you want to.
Yes.
Okay, let me write it like this.
F is again F.
Okay.
F is F.
Yeah. F is F. Okay. So why is this good? Let me consider the sequence. Given by restricting S.
So do we assume that this is cut here?
No. But this is the thing. Okay, so I'm going to define the image of this map. So okay, definition gamma is defined by taking kx plus delta. I can restrict to S, and I get Px plus something else. And then something else by tangent is effective, because this one here. And also, of course, this map is not subject in general, but I'm going to define the image of sigma m. It's going to be defined as the restriction of Px plus delta to S. I mean, this is just this symbol here is just a definition given by this. Okay. So let me denote by R. Sorry, let me give a name to this one. This one I denote by R. And I denote by R is equal to S. It's exactly equal to the sum of all these vector spaces. So it's the algebra given by all these elements. So you see, since S and Kx with delta are more or less one multiple of the other, it's enough to show since the difference comes from Z, it's enough to show that this algebra here is finely generated. Okay, why is this true? Because assume that the image is finely generated. So what this says is that the section here are coming both from something which is finely generated, so it's okay. So some polynomial, some fixed basis, or something which is of something completely different if you look, I mean, at the very beginning, but since I'm assuming that this is true, it's actually an element of the same algebra, up to choosing the number correctly. I mean, of course, I need to play a little bit with the integers, but after choosing the integer correctly, it's easy to see that, I mean, this one is the same as this one. Okay, so it's easy to show that once we show that R over S is finely generated, then we're done. Okay, what would be the dream? The best case scenario, which was almost never true. The best case is when sigma m is subjected for all sufficiently divisible n. Okay, in this case, the restricted algebra is nothing but so I'm looking at so MKX plus delta is to S would be so it would be just this one here. So it's the algebra generated by this section. I should say that I'm not going to spend all the details. I'm not going to talk about all the details, but by inversion adjunction, the pair S gamma is scalarity. So this one is finely generated by because we're on surface. And on surface everything's okay for what we don't want to talk about. Or if you want, we are proceeding by induction of dimension. So we assume that the lower dimension everything's okay. And so we have nothing to show. We show exactly what we want. But this is almost never true. Even in characteristic 0.
So a stupid question, why is the finite generation of that ring enough?
Oh, because you see you have, let's suppose that these one are exactly the same.
Yes.
S against with delta. So what we're saying is that a bunch of sections here.
Well, you're essentially dividing up Cartier principle.
Yeah, exactly. So what I'm saying is that everything comes from either lower degree or something just finely generated. So a combination of this will give a basis of.
what you want.
So you see, the problem is that this method doesn't work, even in quantity 0. There is no way we can apply, I mean, because of this m, there is no way you can say, let's study each one, because there is not only kx. If there was only kx plus delta minus s, it would be business. But since of this m, and kx plus delta is non-f by assumption, there is no way to apply chromatographic explanation directly. But the idea of Shogurov, which was very much developed by Bickel and which was one of the steps to prove differentiation in quantity 0, was, I'm going to make a little bit vague here. So over C, this is again due to Shogurov, and then we can now in details like Bickel. What they show is that using vanishing theorems, so chromatographic vanishing theorems, so neither star theorems, was, let's forget about, this is too much to ask. But maybe there exists some variational model, so proper variational model. Actually, what they proved is in general, not only for surfaces. Such that, in some sense, if instead of working on S, we work on T, so let me just write R restricted to T is 5 meters. Sorry?
What is R restricted to?
So, the idea is that you take section which come from a model, so it's like all the sections that come from T instead of S.
So you just replace S with T and
Not quite, yeah, the work is a little bit more complicated. But as a first approximation, let's say yes. Let me just say that all the sections that come, because the problem is this, if you take the full ring, it's not going to be finely generated, but it's possible that some subalgebra is what Shogurov calls saturated and gives you enough section to be finely generated.
so you replace S with T and probably you replace gamma.
Yeah, you replace, unfortunately it's a bit more complicated. You replace gamma by some gamma m, which depends on m. But they're good enough to be finely generated. But yeah, the idea is that it's almost like an algebra of this form here, for T instead of S. The problem is that it will depend on m, but nevertheless, the way it depends on m, it still allows us to conclude that it's finely generated. Because we can compute how it depends on m. Okay, and the main idea is that we can apply a feature. Okay,
And this variational morphism, is it canonically constructed in some sense?
in some sense, yeah, it's actually the terminalization of some pair, S gamma. So in other words, you almost make S gamma to be terminal. You go to the terminal model, which means to extract all those divisors which appear with coefficient between 0 and 1. So yeah, but anyway, it's a very explicit construction. But it's still, there's a lot of work here. I mean, there's really a lot of work in this paper. Yeah, I mean, in this paper. Okay, and there is also as much work in the paper of Ekman and Schön. So I guess this is step 3. So I'm going to be very sloppy. Actually, I look at the year. I was wrong yesterday. The year is 2013. I will be a little bit vague, but I will just say that the idea was, and again, there's really a lot of of work because replacing commutative expansion theorem requires a lot. But the idea is to replace commutative expansion theorems but by the theorem which was proven by Iromo a few days ago. So by lifting theorem for S. So Iromo proved something like that. I'm just going to copy what he proved. Where M is exactly what I Kx is that. So this one will be Kx as delta sample. Exactly like in the philosophy of the commutative function theory. But what I really want to say is so I don't remember the notation that you don't use, but more or less it's this one. Okay. What is important? What is important is that this is not the end of the story. Why? Because first of all, we haven't used P greater than 5 yet, or standard coefficient. But the main idea is that we don't know. This could be very much empty. I mean, it could contain very little section. This is containing some H0. But what we need to show is that there is not much difference between H0 and H0. So the main ingredient is that, although, of course, this is just one of the little steps in the whole proof, is the fact that this is a theorem proven by Ara. If S gamma is a guilty surface where gamma has standard coefficient, and let me just say, I guess it's clear for the one, P is the characteristic of the field where we're working, and P is greater than 5, then S gamma is not the third.
I thought these theorems of S0 proved in the projector context. And here S is not a projector.
No, they're all, yeah, they have a relative version. They have, yeah, so Taken and should have a relative version. So what is important is that it's relative projective over Z. So they have an extension of the theorem, etc. But yeah, exactly, yeah. That's the only important. It's a bit like going from commutative expansion theorem to the relative keys. It's pretty much like using the same idea. Okay, let me comment why this is good enough. Very, very briefly. I should say that if delta is of the form S plus B, let me give a name to this set. So let me call this set Sn, where B belongs to the standard set, the set of standard coefficients. Then also gamma belongs to the same set.
So this depends on M, Sn.
Oh, sorry. You're right. Yes. No, absolutely no. Sorry. So this is true in any dimension, but actually it's a two-dimensional problem because the diff is defined into dimension 1, so you just cut by enough per surface and you get the surface. So this is pretty standard. So in other words, we can really apply this theorem if you assume that P is greater than 5 and this is true. So the idea is that this implies that after much work like in Hickman kernel, S0 will be equal to H0 in some order. And this is good enough to get final equation. So this is somehow the heart of, I mean, although of course there's a lot of technical issues, but this is why we need the standard coefficient and we need P greater than 5. if you remove any of the two hypotheses, whatever is written here is false in full generality. So I should say, so the fact that this assumption plays a role only appear at the very end of the paper, like you should. Let me give. So very briefly, together with Gongyo and Schmidt, we prove a very similar result, but which does not depend on, so without a restriction on gamma. But of course, assuming that P is back, sorry, so the resist P depends on the coefficient of I. Coefficient of gamma, such that if P is bigger than P0, and X gamma is P of T, then it's also stronger further. So at that time, this allows us to prove this is also pretty. Oh, maybe remember. At the time, this allows us to prove existence of flips for P big enough. And also, immediately after, Bilker proved that you don't need this anymore, meaning that flips exist for any delta, for any x delta, if P is bigger than 5. So the two proofs, so of course this result is much stronger, but the two proofs are completely different. This one still used from left regular theory, instead Bilker's proof does not, it's really an application of the name of the program plus Aikman Schulze. Okay, I would like to comment on this a little bit, because one would like to say, okay, is there something similar in higher dimension? Sorry, I would like to comment on this a little bit, or any kind of generalization in higher dimension. And the answer is false. I mean, the answer is not. Meaning, it's not possible. We cannot, it's really false. We cannot generalize. Higher Steven in higher. So this is an example due to myself, Tanaka, and Itachi. It's very simple, but it took us a while to find it. If we take the germ of this singularity, s cubed plus y cubed plus z cubed plus w p plus 1 equal to 0. Of course, inside A4. Of course, I'm talking about a field A of characteristic P, or at least the same as this. Then it's very easy to check that it's canonical. And it's also possible to check it's not Sunday federal. So I never defined canonical, but I guess all of you know, but in particular, canonical is much weaker than QRT. So even assuming the singularity are much better than QRT, there is no P which will allow to say that, even chasing gamma to be equal to 0. So there is no P that is good enough to say that QRT implies counterfederal. So clearly these methods are falling apart because of example like this.
So even for P equal to
Even for P, sorry?
equal to 2.
Yeah. Yeah, because the two of course things get even worse, but
just the whole of
political, some, yeah, sure.
I think it was only what for P rather than maybe 5 and also P is module 2 P1. So I don't know, module 3
No,
P
no,
is
that's
equal-
the way we work with this without an assumption. That's how we work it. Oh no, you're right, sorry. Sorry, that's a problem. Thanks, sorry. Well, so P might be equal to 2 modulo 3, sorry. You're right, because it's not a fair right, so thanks.
I think P is rather than 5 or something.
Really, otherwise it will be stronger further.
P plus 3 is already a problem.
No, but P cannot be equal to 3.
So it's 3.
Oh, maybe.
Yeah, it's okay. Okay. I would like to mention many of the results that there's been quite a lot of progress in over the last 2-3 years. After the work of Ekman and Schur, I would like to mention some of these results. So let's see. So I already mentioned the result of Birker, and let me say that slightly before, myself and Schur proved that the principal theorem holds for P big enough in relation to it. Oh, well, let me just be careful. For P big enough in dimension 3 for the dimension 1 and 2. So let me just say this was doing the same period a little bit later than I didn't rely on Schur. But let me just say one thing is that Kiel proved the basement fit theorem for codal dimension equal to 3 for the big case. By the time of Ekman and Schur, the basement fit theorem was still not known in the full generality. And actually, Kiel's theorem proved only a partial version of basement fit theorem. It only proved that over a field of positive characteristic, it's endowed in the map. So actually, Birker and Schur independently proved that the same result holds for the big case. And P big result. And then,
much greater than 0 also means some particular value, or
so it depends. At the time, it was based on the coefficient of the device of A. Now it's been improved. But it was 2 over A, where A was the minimum of the coefficient that appears in the boundary.
so it's not universal.
No, at the time, no, but now it is. I mean, this was in 2015. I think this is 14. Okay. So Birker and Waldron proved the full generality for P bigger than 5. But again, what they do is to not use, here I will mention some of the results related to this paper. But here they don't use any strong left regular property, they just use it as a constant frequency. So if you look, the reason why I want to talk about the history is because the way the logic works is very weird. Even if up to now, the only way to prove this kind of theorem is to first prove Kiel's theorem, which is a weak base frame free theorem, then prove existence of fields, and then prove base point free theorem for p greater than 5. So it's very, very, let's say, not a direct proof, because you need to work first a weak version, then a big theorem, and then another time. So I'm pretty sure we're missing something. I don't know exactly what. Okay, so very briefly, because I'm running out of time, I will mention a couple more results. So, Waldron profile variation holds for 3 folds. In dimension 5. In dimension 2. All these results rely very much on the geometry, that's why p greater than 5 is always in use. And then let me just say, out of laziness, that Waldron, that's Waldron. And then independent design prove a weak version of balance. So for instance, abundance in the case numerical integral is still open in dimension 3 as far as I know. Okay, so, and this one is very much in the last few years. So if I'm not wrong, this is both of these results in 2016. And this is also 2016. Okay, I would like to talk about higher dimension now. We know very little in higher dimension, but nevertheless, and not everything looks extremely positive, but we know some version of base point free theorem. So the theorem which we proved together with Tanaka, Hiromu, and Shinichi was, now we're not assuming n to be equal to 3 anymore. Let's suppose that x delta is a stronger Federal pair. So I suppose projective. But here we need to be a little bit careful. So in any dimension. I'm going to use a stronger version, and we'll be clear 1 minute why I care. I'm not only assuming that this is a Q divisor, but any R divisor. We never talk about R divisor. But the definition that Hiromu gave is exactly this, works exactly the same by taking some round down. So this is just some generalization. And the reason why it's nice to generalize will appear in 1 minute. So let's suppose that A is an ample R divisor. Such that Kx plus delta plus 8 is strictly F. So this word appeared a few lectures ago, but I'm not remembering what it means. So it means that over any curve is positive. So this is the definition strictly F. Of course, it's much stronger than F. Then Kx is delta is ample. Then Kx plus delta plus A is ample. Okay, as an exercise, you can check that this is a consequence of the base point free theorem. Why? Because if it's base point free, if it's semi-ample, it means there is a map that contracts all the curves on which it's zero. But there's nothing to contract it because it's strictly ample. So automatically it will be ample. So this is, let's say, a very special case of the base point free theorem. But still, it has a nice application, which is very easy to prove.
So the real coefficients, ample is simply going to be defined in terms of being strictly positive on the closed cone.
One way to do that is correct, or the way to do it is the ample cone, it's open.
Okay.
So a little small perturbation would be ample. which I already mentioned a few lectures ago, but we never proved. Let's suppose that x dot is not Lefebvre, but now I really assume that that is fractional, otherwise the address is true or false. That is a Q device. So of course it's within 0, 1, because otherwise you normally start with that. And let's suppose that A is an ample Q device now. So one of the ingredients, unfortunately it's not the only ingredient, of the cone theorem is to consider the net threshold. So it's the infimum of all the t such that kx plus delta plus ta it's net. So this is the definition. Under this assumption, lambda is a rational number. So if you remember, when we apply the name of the program, what we do is to take something which is not f, we take an ample divisor, and we go all the way until we stop at the threshold. So it's nice to know that it's rational. And actually, the cone theorem, one way to prove the cone theorem, the strongest version of the cone theorem follows from this result plus bounded denominator of lambda, but which we cannot prove. That's why we don't have a cone theorem in one dimension. Okay, how are these two results related? So the proof is very simple. First of all, I can assume kx plus delta is not f. Why? Because otherwise lambda is equal to 0, and for sure it's rational. Okay, so let's suppose that lambda is positive. And actually, I'm not going to use the fact it's positive, but it is true. But I need to use the fact it's not. So, and kx plus delta plus lambda a, it's nef because the nef cone is closed. So being the minimum, the infimum within nef divisor is also nef. But it's not ample because the ample cone is open. Because again, being the infimum of nef divisors, of ample divisors will be, well, it wouldn't be anything. So this is a very silly mark. Okay. By the theorem, you see, until now we don't know anything about this guy. We don't know whether delta is a divisor. Oh, well, sorry, delta is a divisor, but we don't know A is an O. It's a Q divisor. So I really need to either assume delta or A is a divisor. But we know that kx plus delta plus lambda A is not strict in F. Because if it was strict in F, this would be ample. Okay, what does it mean to be not strict in F? By definition, there must exist a curve on which it's 0. And this is the end of the proof. Why? Because it's a linear equation. It's a non-trivial linear equation. So, A times C is a rational number, kx plus delta is a rational number, times C is a rational number, so automatically lambda would be a rational number. Okay, so that's one consequence. So let me just say one more results toward the base pair field theorem in any dimension. So before, it's very similar to this theorem, but in a slightly stronger generality. So L is called an F lemma of L moving curve, movable curve, which means that it lives in a family, algebraic family which covers the whole variety X. So after this definition, the theorem, which is due to the same people, CPX, but also proven independently by James McCurtain, although it was never finished, I think, is the following. So let's suppose that now we assume very, very little about the singularity. In particular, X is supposed to be only normal. Of course, everything is in positive characteristic. Otherwise, what I'm going to say, it's already known. A is an amplitude divisor, or R divisor. And B, now I'm using the letter B, just because it's not the option. It's any R divisor, without any assumption on the singularity. It's not a big deal because it's a generic assumption, such that X plus B plus A, it's R here. Which means that some real multiple X plus B plus B plus A is factorial. Of course, I need to tell you something more on this. Okay, so if it's occurred here and the maximum left dimension, and length of maximum left dimension. That is good. Okay, again, this is not true for any divisor without the assumption that it's of the form X plus B plus A. And again, it's a consequence of the base point free theorem. Why? If you take a singularity, because if you are in a good singularity setup, this should be semi-ample, but it's a positive on any moving curve. So the only way for this to be true is that the map associated to Kx plus B plus A is birational, which implies that the device must be big. So both the theorems were proven by, I'm talking about our proof, not James' proof, were proven by using some method that comes all the way to Hanger and Seal. So trying to take zero-dimensional open-order centers, but I'm not going to expand. So it's still related very much into strong differential singularities, but it's replacing Hanger and Seal's method with this setup. So I'm not going to talk about the proof. Okay, very, very briefly, I would like to say final words about. So my last lecture was supposed to be about base point free theorem, cone theorem, and law of the Pezzo. So I'll talk about very little about law of the Pezzo. I think Roman talked about it a bit yesterday. I'm going to talk about something slightly different. So what is a log that Pezzo is a log final dimension group. So in other words, X delta is log that Pezzo if it's DLT, if it's projected of course, it is DLT, and the minus Tx is delta, it's M. So something that appeared not completely in this way, but in yesterday lecture, is that we expect vanishing theorem to be true in this setup. But it's not true in small characteristic.
Which is one definition. Can you explain just numerical level? Is
Okay, so what we know that is not true is that Kawata fever does not hold. I mean, we know that this was explained by yesterday by Romo. Kawata fever fails. It is pretty good. And this led us to construct, for example, too many of the things which were assumed to be true by the minimum, which are supposed to be consequences of the minimum of the problem. But I would like to talk about what about if it's very large. So this is somehow a little bit resemble what we were talking about before in Hara's situation. Hara said that if a surface has P large, then KLT is the same as from Lefebvre. Now we're in the global setup, so we would like to know whether log de Pezzo is the same as global Lefebvre. So let me just, I think it was mentioned actually, but I'm not sure. Let me just recall or maybe note that if X delta is global Lefebvre, then come out in the fraction holds, at least in this picture. This left, then left and up, okay, then HI DXT is equal to 4 plus 2. Okay, and this again is a consequence of the chromatic variation theorem. Now the question is, under what assumption del Pezzo implies global infrared? Exactly like in Hara's theorem or in my theorem in complex field. Can we say that if P is big enough, and this was our motivation, can we say if P is large enough, then global infrared is the same as log funnel? So this is the question. Is it true that if P is very big, whatever it means to be very big, then being log to Pezzo is the same as being global infrared? As Romeo, I think, explained that this one is always true. But the other way is not, is by far not true because it's even KLT does not compare to the Okay, so the answer is no. And this again was proven by, I mean, we found that, for example, with the same result before. But there is not only bad news, there is also good news, which is simple. Even if it's not true, it's almost close to be true. So there exists, let me just read this copy. P is 0, such that if P is bigger than P0, and X delta is log de Pezzo, then two cases can appear. Then maybe both of them, so I'm not going to say either or. But at least one is true. Either X delta is log de Pezzo, or there exists a log resolution of X delta. I'm going to be very slow here, but I will explain what it means, which leads to characteristic 0. So we're not saying only that the resolution leads to characteristic 0, but both the resolution and the exceptional locus leads to characteristic 0. And this is important for what I'm going to say in 1 minute.
So just a P0 independent of everything.
It depends on the coefficients. Sorry, should I say?
Coefficients of
Delta.
Ah.
Yeah. It must be the case because otherwise it's not going to be even KLT. So let me just check. Yeah, sorry, P0 depending on the coefficient. Okay, and a very, very last statement I would like to make as a consequence is that this is almost true for local pretzels. In other words, and the proof is very simple. Oh, well, it's not very simple, but not hard. So as a corollary, and again, I'm going to be very vague. Quantitative vanishing holds for local pretzel. If this big enough. And again, big enough means depending on the coefficient. What is the idea of the proof? It's not completely straightforward, but the idea is that by this theorem, either it's globally regular and then there's nothing to prove, or at least it's a consequence of this kind of results, or there's a representation of the lift bracket is 0, which is big enough by result of mathematics, to show that vanishing holds also in our local sets. So, yeah, it's a good time to stop. Thank you very much.
Questions, comments? I have a problem about MLT in dimension 3. How about versions of this MLT? For example, over non-closed fields or direct group actions, something like this.
Okay, group action, I don't know much. I don't think that anyone did it. I don't know anything for group action. I don't know anyone. I know that some people think about that, but I don't think I've seen anything written about
What's the
it.
problem here?
Sorry?
What's the problem?
I think no one ever tried. Because as I say, most of the results are very, very recent, in the last 15 months. So I guess it's usually need to assume that P might be independent of whatever we do. I'm not sure. I really think that anyone has tried. It's possible that there's no problem with it. I know that some people are thinking about that, but it's a very, very big deal. And that's what the proof is. So I don't know anything really now. And the second question was not algebraic equals field. That's a much more difficult question because yeah, it's too good